Okay folks, we're back again with our Heathkit IO-4205 oscilloscope, and we're going to proceed on. Now what I've got it set up here. I've got a 10 kilohertz signal at 20 volts peak to peak going into both channels. I'm only looking right now at the screen here. I'm only looking at the channel of interest, the one that has the poor performance, and you can see that clearly there. And but you can see now I'm probing right at the input here on the oscilloscope, and you can see that is a nice square wave is going in at that point. Now the next thing we've got to do is get somewhere over here, try and see if we can pick up the signal at this point and see if it's degraded at that point, and then we'll go on to the next point. Now I have a funny sneaking suspicion if we're going to find the problem, it's going to be right there. With this capacitor and tuning capacitor here, this pair, because that's the range that is giving us the problems when that is switched in. So, but let's have a look down along the line here. Locating all the different points is the tricky part, but we'll try to do our best here. Okay, so let's go on to the next point along the line. This is where we're going to go next, is R101A. We want to go to the top of that. Now this is the first resistor in the attenuator circuit. So we'll have a look at the signal at that point. It should be pretty much exactly the same as what we saw before. And it is. So that's good. Now go to the other side of that. Alright, so let's see what that looks like when we switch up to there. So that's when that resistor's in circuit. We got a good signal coming out of it. But the point of note is going to be over here. Now this is where I suspect we're switched in there now, and that's pretty much what we're seeing on the scope here. So that's where the problem is, and it kind of goes away if you switch that out of the circuit. If you switch into a different part of the attenuator, there could be some compensation done there, but that's a heck of a lot better. And if we go back down to this part of the circuit, you'll see picking up a bit of noise there, but I'm sure that's filtered out, so that's not quite as bad. That's the upper end, which I think has been designed because it's in both channels, so it's a part of the design. But this here is not. This is not in the other channel. Now I can't adjust that out, so if I take this capacitance here and get rid of the oscilloscope for now, no matter how much I adjust this, now rotating it this way is supposed to reduce the capacitance. I can't reduce it any further than it is, and I think I know why. Now, if I increase it, it just gets worse. But this tuning capacitor here actually looks damaged. Something happened to it. Now these tuning capacitors are made by, they have several little plates together with insulators in between them, and as you screw down on those plates get squished together, and as you unscrew them they come apart, so that changes the capacitance. This looked like it's received a serious amount of pressure, and somebody was cranking on it to try and get it to work properly. So at this point in time, I don't think it can't come off enough to compensate properly, unlike this one over here, which seems to be in fine shape. So what I'm going to do, and just a wild guess here, if I can't reduce the capacitance enough by unscrewing this, I'm going to cut out that capacitor that's across it. So right here on the schematic, we have this other capacitor here. I'm just going to nick one of the legs off of that and see if that gets us closer. It might drive us too much in the other direction. I may have to replace that capacitor with something in order to make up for the damage done to this trimmer here. But let me find out which one that is, and we'll cut that leg and see what that does for us. Okay, that capacitor is this one right here, C105B. and it's a 330 picofarad capacitor. So let me just, I want to power this thing down for a second. Just nick the leg on that. All right, I should be able to solder that back up if indeed this doesn't do the right thing. And let's turn it back on. And okay, so it's obviously it's going the other way now. So it's undercompensated. Let's see if we can, or overcompensated, whichever lingo you want to use. Okay, so now I can get that straight. All right. Okay, I think that's the best we're going to be able to do there. But that's quite good. That is quite good. Let me see, how does that compare to channel 1? On the same level of attenuation. Move it down. Okay, it's almost exactly the same. All a matter of compromise, I guess. So those very lowest ranges look pretty good. It all depends on where you see yourself using the scope the most. But so yeah, it's not looking pretty good. Still just those highest ranges that are a little bit sad. Well, I'm good with that for this scope. I'm going to leave that off there. If I can ever find one of these trimmer capacitors, I might replace that one and then resolder that into place. Well, I'm going to call that a success. And what I'm going to do now is take a quick look at the horizontal side. And so let me set up for that and we'll come back. Okay, here we are set up to do the horizontal adjustments. Now they're asking us to put in 5 kilohertz and set it up for 200 microseconds and adjust it so we get exactly 10 oscillations on the screen, and we can see that we're getting a little bit more. Okay, so this here is the calibration control. And I don't think that's enough. Oh, got it. Okay. Now, I'm going to call it done. I mean, this, it is a very old oscilloscope. It's only a 5 megahertz oscilloscope. And it'll be fine for looking at waveforms and for, just checking things out. It's not totally inaccurate. The horizontal time base is now pretty good. The compensation on the attenuators is not too bad. It's improved that considerably from what it was. And at this point, I think I'm just going to put it back together. Or maybe what I should do is try to compensate some probes on it. Put everything nominally back on a level playing field here. I've got these nice pico probes that I'm going to use for this scope here. They're 200 megahertz probes, and they have quite a good compensation range on them, so I think they'll probably do okay. So switch them on to times 10 and compensate one for channel 1 and one for channel 2. Okay. So I've got 1 volt peak to peak going in. The probe is set to 10 times. That looks pretty well compensated to me. A little bit off here, but that's going to change, as we go through this attenuator here, as we've seen. So let's adjust that little bit there, see what that does for us. I think that's good enough. We're about 1 billion times better than we were before. Okay, now let's go over to channel 2 and we'll compensate a probe for that. That one looks like it's pretty well compensated already. Wait for for use on this scope here. I think it'll be fine. Okay, I think I'm going to just put it all back together again. Alright, let me do that and we'll come right back. Okay, here we have it all put back together and put in place. But one unfortunate thing is, by the time I had gone through all putting it in place, the trace has really gotten skewed. Anyway, what I'm doing with it here, now that it is at least compensated properly, and is I've got a little crystal here, one of those little clock crystals, the 32,768. That's not focusing on there very well, is it? Crystal, and I just got it in a series circuit here. I've got Siglant waveform generator here. It's putting out 32,763 hertz, which we pretty well verify over here on the frequency counter, and that seems to be the point at which this is in this particular circuit here is resonating. So if you go off just by a few, let's say I take it down to, or put it up to 32,780, it's off. We bring it back down. This is what it's supposed to be oscillating at, but I guess the loading here with the scope on it is throwing it off a little bit. But now we can see as it begins to tune here, I think just right around about there is a sweet spot. So about 32,763 hertz. And if you go a little bit too low, like 750, it's gone again. So the crystals are pretty resonant at one particular frequency given the circuit that they're in. And this one is resonating here nicely at 32,763, and the scope is working really well. Other than, of course, the trace being a little skewed. I'm not going to worry about that for right now. Someday when I have very little else to do, I'll be more careful about taking it apart, setting that, and putting it back in the case. But I'm quite happy with what we're able to do. Get this thing working much better than what it was before. We've got the time base settled. We've got the vertical compensation settled for the different attenuator ranges. And it's not perfect by any means, but I mean, for the kind of scope it was, I don't think it was ever meant to be perfect. I think what we got is about just as good as anybody would get with a new one. Possibly some of the parts have aged in there, and I'm not going to go and pull those out and replace them at this point in time. It's just, I just got this scope, as I said, for nostalgic purposes, and it'll be a great little scope for looking at low frequency waveforms. It might get some use up here on my vintage bench, but I feel that scope probably going to get a little bit more use than this one, but it looks so cool. I love it. Anyway, thanks guys for joining me again. We'll see you in the next video. Bye bye.